Welcome to week 9. So we're going to start talking about multiple linear regression, which is expanding off of that simple linear regression. So last week we looked at two variables, usually two quantitative variables, a response and an explanatory. Multiple linear regression just introduces more than one explanatory variable. So you have one quantitative response and multiple categorical, well, they don't have to be categorical variables, but multiple explanatory variables. So consider this example here. It's a little dated. I'm sorry about that. One of the, if you look at the scatter plot, they're looking at body fat percentage versus daily activity, so average daily activity in minutes. So they asked folks, okay, on average, how many minutes per day are you actively exercising? And recorded their body fat percentage. It's in percent. So if they had a 25%, it would be at 25. Wow, I circled really badly. So it's a small sample here. There are 14 individuals in the sample. You can go ahead and double check by counting the number of dots in the scatter plot. So looking here at the scatter plot, if we want to describe the relationship here, you can see that first off, well, there is a strong negative and linear relationship between average daily activity and body fat percentage. Note that later on we might abbreviate average daily activity to ADA. So here, further looking at the slope coefficient, which is not shown here, the least squares regression line, when you fit it to this model here, is that for each additional minute of average daily exercise, the average body percentage is estimated to decrease by 0.283%. So a little more than 1/4%, it's expected to increase for each additional minute. So one additional minute is probably not going to make a big difference. 15 minutes, 30 minutes, 60 minutes, that'll make a bigger difference. So what we want to look at here is now they've broken it into sex. So they have people identifying as men and women here. The women are the triangle, because F for female, M for male. I know this seems kind of weird, but basically 0 and 1, the one that comes first alphabetically, which is female, that's the one that's 0. The one that comes second alphabetically, which is male, is 1. So looking here, you definitely see downward trends for both groups. Although it's worth considering that maybe for each additional minute of activity, the decrease in body fat percentage is different for each group. So given the same amount of activity, so if you have men at a certain level of activity and you have women at the same level of activity, it looks like men are estimated to have 3.18% less body fat than women on average. Note, this is a very, very small sample. So that is worth noting. So we have an updated model here. So estimated body fat, so this is still a y hat, is equal to, we still have a y-intercept estimate. So minus 0.297 times the amount of daily activity minus 3.18 times sex. So sex, note that sex 0 is female. So if the person's female, you plug in a 0. 1 is male. And that's strictly because F comes before M in the alphabet. That's typically how the software works. It's going to assign whatever comes first alphabetically a 0, and then assign the rest in alphabetical order. So comparing simple linear regression versus multiple linear regression. So this right here, that was our week 8. That's what we looked at last week. So it models the relationship between two quantitative variables. So we have a quantitative response variable and a quantitative explanatory variable. This week we're looking at multiple linear regression. So we are going to look at the relationship between one quantitative response variable and multiple explanatory. So the explanatory variables, they can be quantitative. Usually at least one will be. They can be categorical. They can be a mix. So it's worth noting. So they can be either. And binary explanatory variables, we tend to call them indicator variables. So, for example, that in this right here, this sex variable, it's a 0 if it's female, 1 if it's male. Very dated example there. That would be an example of an indicator variable. So 0 basically says, hey, this condition is present. 1 says it's not. And if you have, if it's something that is not like a yes or no type question, it's just going to put it in alphabetical order. So the estimated regression equation. So it's an expansion of what we were looking at last week. We still have y hat. We still need to define what that is when we're describing it. So y hat is equal to, in this case, estimated body fat percentage plus B0 plus B1 times X1 plus B2 times X2, all the way through however many variables you're adding here. So in this example, we have the average daily activity and we have sex. We're only going to have just this part right here. However, you can have more than just 2 explanatory variables. You can have many. It kind of gets overwhelming if you have a lot, especially if you have a small sample size. Definitely know that you never ever want to have more variables than you have observations. It will perfectly fit everything, but it'll almost be like every single point is its own thing on here, and you don't want to do it. It's a very useless. It becomes a very useless equation if you have too many variables, explanatory variables. So B0, B1, B2, and so on, they're all unbiased estimates for the population version. So the idea is if I were to take all men and women in this particular population and fit a line of average daily activity by body fat percentage, I could come up with population, like this would be the y-intercept of the population line. This would be, the slope that goes with this coefficient of the population line, and so on. And so what's really great is B0, B1, B2, all of those, they're unbiased. So that means on average, they're accurate. They're accurate estimates for beta 0, beta 1, beta 2. And then y hat, that's going to be the average response for a given set of explanatory variables. So in this case, you might have somebody who has 60 minutes of daily activity and is male. That's a specific set of explanatory variables for this example. So recall, in simple linear regression, it was simpler because we only had one explanatory variable. So it's simplified to y hat is equal to B0 plus B1 times whatever the explanatory variable was. So we use a method called least squares to find the values for B0 and B1, B2, and so on. And here's an equation for it. We aren't generally going to ever expect you to calculate the square differences, but the idea is we're taking the difference of what's observed in the actual sample, we're subtracting what the line equation estimates that y will be given those. So if I said, hey, you know what, here's a female individual with 60 minutes of daily activity, and this is their body fat percentage, this would be their YI, the actual body fat percentage we actually observed, minus what the line estimates their body fat percentage will be. So we take all those differences and we square them. And so this is doing exactly what was happening in simple linear regression. It's making as many points as close to the line as possible. It's trying to make the spaces between the points in the line as small as possible because we want the line to be simultaneously as close to all of the points at once as we can get it. So these residuals are that leftover variation. So our least squares regression line is making an estimate like, hey, here's where y hat is. Where is the observation? How far from the line is it? And ideally, you want to make this as small as possible. So estimating variation. So we talk about sigma. It's how spread out are the observations around that line. So it's the standard deviation of the response variable about the predicted mean. So it's really asking, well, how spread out are all of the observations around the line? And we do assume that it's the same for all values of x. So we assume that for, if we're looking at the body fat percentage one, that for low daily activities, medium daily activities, high daily activities, we're imagining that spread around the line's roughly the same. So the mean squared residual is what we do to, it's known as S squared. It's our estimate for sigma squared. So if I want to estimate sigma, I will use S, which is just the square root of what's called the mean squared error. So we're squaring the differences between every observation in the line. And it has this lovely equation. We, in general, will never expect you to calculate this by hand, but we want you to know where it comes from. That's the important detail. We will be able to get this value from the output, that software output that we give, and we'll show you where to get that. So looking at this equation though, n is going to be the sample size. So like in the particular example we're looking at with the body fat percentage, we have 14 individuals or 14 observations. So n is 14. And p is going to be the number of explanatory variables. So in this scenario, we have the average daily activity, and we have sex. So before we get to testing those individual variables to see, oh, is this variable useful, is that variable useful, we are going to ask a more general question. We're going to say, are any of the explanatory variables useful? So it's kind of like a, hey, are any of them useful? If you say that at least one of them is useful, then we will proceed and try to find out which one or which ones are useful. If you say no, this overall F test finds that none of them are useful, we're probably going to leave it at that, right? Why find which ones are useful if you found that none of them are? So an overall F test, it tests that, hey, is at least one of the beta coefficients not equal to 0? So here is going to be the null. So beta 1 is equal to 0. Beta 2 is equal to 0. If we're looking at the body fat example, because there's the one that goes with ADA and there's the one that goes with sex. And you'll go through as many betas as you have. In this case, we only have 2, but you can have many of them. It shouldn't be bigger than your sample size ever. It shouldn't be equal to your sample size either. That would be bad. And then your alternative, at least one of them is not equal to 0. It doesn't matter if both of them are. If at least one of them isn't 0, that's good enough for us to reject the null. So if we wanted to put this in kind of layperson's terms, it's like saying, hey, is average daily activity or sex, is at least one of those useful in predicting body fat percentage? The alternative will say, yes, at least one of them is. It doesn't say which one, but it says, yes, at least one of them is. So F-test, that means we're going back to that F distribution. So most stats software, they'll go ahead, they'll give you an F statistic and a p-value. There are such things as F tables. They are somewhat more complicated. We're probably not going to get into giving you an F table and expecting you to give us a p-value from it. We're much more likely to just give you like a software output table. It's one of those old school skills, like I happen to know how to use an F table, but incoming stats majors usually, they're not being necessarily trained to read F tables. It's an old time skill. So it's going to be skewed. It actually reminds me of the chi-square distribution a little bit. Except for, it doesn't have one set of degrees of freedom, it has two. It has a numerator degree of freedom and a denominator degree of freedom. And these are Greek letters. Like, I want to say it's nu 1 and nu 2. They look like funny V's. But, so 1 and, they look like confused V's. Nu 2. I don't know. It's not my favorite Greek letter. As long as you, I usually write NDF for numerator degree of freedom and DF for denominator degree of freedom. I find that more useful than writing nu 1 and nu 2. So in general, if you have an F statistic of 1 or lower, you're going to have a huge p-value. You're going to find that, you know what, those variables aren't useful. The further it is from 1, so not just further, but bigger than 1, that's going to definitely indicate, hey, at least one of these are useful. How much bigger than 1 is going to depend somewhat on your degrees of freedom. It depends on the combo degrees of freedom, what your p-value is going to be. So here's an ANOVA table. It's analysis of variance, ANOVA. That's where all those parts come from. So in order to do that, we have our ANOVA table. We're going to have a place that says source. So regression, this is going to say, hey, this is, the model. This is going to be, what's explained or what's left over, whatnot, like from our, specifically our model. So the explanatory variables. What do the explanatory variables help explain? Error. So this is saying what's left over, what's not explained by the model. And then total. So looking at this table, I definitely strongly recommend having this written out somewhere. This is not something we necessarily, we definitely don't expect people to just memorize this, but you should be able to kind of use this table. P is going to be the number of explanatory variables. So right here, this will be the number of explanatory variables you have. For me, one thing that's really, really cool is you add down. So P plus n minus p plus 1, you get n minus 1. So for me, I say, okay, well, the number of variables in my model, and then my sample size minus 1. Those are really, really easy for me personally to find. So I would go ahead, find these two, and then find my degrees of freedom for my error just by taking the difference. So the bigger one minus the smaller one, that's going to be my degrees of freedom for my error. We're going to have our sum of squares for the model. So what the model explains, sum of squares for the error. So what the what's left over, what's not explained. Sum of scores total. So if I add these two together, I'm going to get sum of scores total. So then what's cool here is then you go across. So your sum of squares divided by p. So my sum of squares divided by my degrees of freedom for my model. So sum of scores for the model divided by degrees of freedom for the model. So D, F, I guess M for model, E for error. This would be DFE. So SSE divided by DFE, that's my MSE, which is an important detail we'll bring up later. Then you take the, I cannot, okay, I was having issues erasing, that's just me. Then you take the ratio here. So what's explained by the model divided by what's not explained by the model. That gives you your F statistic. The bigger it is, usually the smaller your p-value gets. Well, actually, the bigger it gets, absolutely your p-value gets smaller. And then the p-value. So you can use an F table. We might mention one, but in general, we're going to give you a table that has this value. Because it's going to be kind of like reading a chi-square table or a t-table, but a little more complicated. So we don't want to go there. So the degrees of freedom for an F statistic are, so my numerator degrees of freedom, that's just P. That's my degrees of freedom for my model, that's P. My denominator degrees of freedom, that's DFE. So that's that N minus P minus 1. So in simple linear regression, P is equal to. So I'll give you a moment. Here's a good place to pause before I explain the answer. So remember, P is equal to number of explanatory variables. So in multiple linear regression, this is going to be 2 or more. In simple linear regression, it's just going to be 1. Simple linear regression is 1 explanatory variable, 1 quantitative variable. And that's, one response variable. And they're going to be quantitative. So here is that BMI example. So things to note, so N minus 1, there were 14 observations in the sample. So 14 minus 1 is 13. There are 2 explanatory variables, your average daily activity and sex. And what goes in between? 11. So 2 plus 11 is 13. Boom. We do not expect you to calculate this row right here. We will not, in general. That would be complicated. But yeah, so you're just going to take that 794.81 divided by 2. That gives you your MSM. 80.4 divided by 11. That'll give you your MSE. Take the ratio of these two. That'll get your F statistic. Use an F table. We're not expecting you to, but that's where this p-value comes from. So from overall, we have an F statistic of 54.37, which is definitely a lot more than 1. And note that whenever we have an F statistic, we always say the numerator degrees of freedom first. So on 2 numerator degrees of freedom and 11 denominator degrees of freedom. Note that sometimes we'll write it more casually. We'll say, oh, an F statistic of 54.37 on 2 and 11 degrees of freedom. It's always implied the one that's first is the numerator degrees of freedom. If you mix them around, we will go, hey, wait, which one's the numerator degrees of freedom. That's what we do. Getting a p-value, it looks small, so I'm just going to say less than 0.001. So we have very, very strong evidence. At least one of the two variables, either average daily activity or sex, is useful in predicting the body fat percentage. So what is the value for the estimate of sigma squared? So remember we mentioned that MSE is the best estimate for sigma squared. So here, this is M for model, this is E for error. You kind of have to line up the weird acronyms like MS and E right there. Oops. So MSE is my best estimate. It's 7.31. That's my best estimate for sigma squared. If I wanted estimate for sigma, so not sigma squared, you want the square root of MSE, which I'm just going to put the square root of 7.31. I'm not going to calculate it here. It's going to be between 2 and 3. I don't know off the top of my head. So looking at the ANOVA table for this example, so we want to test, first off, we want to test, hey, is at least one of the two variables useful? Once we do, we're going to follow up. Like if we say, hey, yes, at least one of them is useful, we're going to follow up with, okay, well, which ones? So looking at this example, we need to start off with beta 1 is equal to 0, beta 2 is equal to 0. You can go ahead and throw in that they're equal to each other. And my alternative is at least one of them isn't equal to 0. Note, if they're equal to 0, it means they aren't useful in predicting the body fat percentage. If they are useful, the betas won't be equal to 0. Things to know. In this case, beta 1 goes with ADA. Beta 2 goes with sex. And that's because alphabetical order. That's really what it comes down to. ADA was put in the model first because it comes first alphabetically. So just if you want to keep straight, if we said, hey, we want a confidence interval for beta 1, we're talking about the coefficient that goes with average daily activity. So performing this, we had this on the earlier slide there. We're going to reject the null because we have this really tiny p-value. So with an F statistic on 2 and 11 degrees of freedom, with a p-value of less than 0.0001 at the 0.05 significance level, because we didn't actually list a significance level. And note, this is an example of me saying, hey, remember, if we didn't actually label the numerator and denominator degrees of freedom, we're going to always assume the one you say first is the numerator degree of freedom. Always. So then we have to translate. We have very strong evidence that at least one of the variables, average daily activity or sex. Sorry, sex and gender are different. Invite y'all to look it up. Are significant predictors of body fat percentage. So we have very strong evidence at least one of those two variables are useful in predicting that response variable. Then we have this really fun thing called the coefficient of determination, which is R squared, which absolutely is related to R, like that correlation coefficient thing, although it's more complicated in multiple linear regression, so we look at R squared. So what you look at is the sum of squares for the model, so what's explained by the model, over your sum of squares total, so everything that there is to be explained. Taking that ratio, you're basically saying, okay, well, what percentage of everything that there is to be explained that's going on is explained by the model. And here are just a couple of equivalent ways to calculate it. So it defines the proportion of variation in the response variable that's explained by the model. So if you look at like the observations around the line, there's some variability, right? So we're trying to figure out, well, how much of that variability is explained by the line and how much is left over, really. So the higher this is, the closer this is to 1 or 100%, the better typically the model is doing at predicting the response variable. So it's definitely very useful in multiple linear regression. It helps us figure out how well the model fits. And it's used to, I mean, if it's really, really low, if it's anywhere close to 0, we probably don't want to, and that's just it. Values range from 0 to positive 1. Values near 0 means very bad fit, very, very small percentage of the variability in Y or body fat percentage is explained by the explanatory variables. If you actually get an R squared of positive 1, that means like it's a perfect fit that, you know, at every point is basically on the line exactly. Usually it's going to be somewhere in between. It's not usually equal to 0 or 1. It's usually somewhere in between. So this is equal to that R squared as the correlation coefficient squared in the simple linear regression scenario. So calculating it here. So we have our model, we have our error, and we have our total. Right? So remember, for R squared, we want SS from the model divided by SS total. So we have those two values here. This one divided by the bigger one. So our R squared here, 794.81 over 875.21. We get a value of 0.9081, which is pretty decent. This is pretty close to 1. I would say there, you know, a lot of the variability of what's going on in body fat is explained really well by average daily activity and sex. So this means roughly 90.81% of the variation is explained by the explanatory variables. So the two I listed. Generally, the higher the fit, the better. And I say generally, there is a caveat, and I will describe that one. It has its own slide of cautions. So, like the correlation coefficient, there are cautions about using R squared. Like, you want to use it, but you want to use it in an informed way. So it needs to be done on a case-by-case basis. There are sometimes certain fields are going to need to have an R squared, you know, maybe 0.9081 is great. Or another field might say, no, that's not high enough. We need a higher R squared to be satisfied. So it depends on the field. And this is definitely worth something noting is you can inflate R squared. You can make it be bigger. You can force it to equal 1 if you just keep adding explanatory variables. So that's like the laziest statistician. You don't want to just keep adding explanatory variables until the model fits perfectly, because then you're going to have too many variables. It's going to be overfit. That's actually a thing that we do. We call it. We don't like overfit models. Basically, the model is only good for describing your exact data, but aren't really good at describing anything else. You don't want to do that. So once you run your overall F-test, asking, hey, are any of the explanatory variables useful? There's a follow-up set of tests. Okay, so at least one of them are useful. Which ones are useful? So then you have your individual t-tests. And this is going to be really, really similar to what we were doing with the slope coefficient in simple linear regression. I mean, it's going to be basically identical. So the null and alternative hypotheses, they're going to be beta and then whatever value goes with, so like if you're looking at, you could even rearrange it. So you could say beta ADA is equal to 0. It might be easier, just notation-wise, for you to keep straight that 1 goes with ADA. If you use beta 1 equal to 0, you need to tell us that 1 is equal to what? ADA. So just a caution there. You want to keep straight like which ones are which. We will calculate a t-statistic. It will be pretty much the same as it was before. It'll be the estimate, so from the table, minus the null value, which is 0, so minus 0. So it ends up being beta j over my standard error for bj. Note that the standard error for any given b can be really tedious to calculate. It's not something we expect you to do by hand. It is something that you can pull from a software output table that we will give you. We will not expect you to calculate this from scratch. It is pretty gnarly. And then if you want to find your p-value and you have a t-table, your degrees of freedom is going to be n minus p plus 1. This will be your degrees of freedom for your error. So if you were looking at your f-test, or your denominator degrees of freedom, it's the same value. So looking here, we're going to go ahead, we're going to test the coefficient for, so the slope value for average daily activity. So here, one, I'm going to list that that's ADA. And if you look here at the statistical software output, so predictor constant, this means, like this goes with beta 0, that's our y-intercept. We don't bother testing the y-intercept. It gets really goofy removing a y-intercept, so we don't do it. Some fields might, but for the most part, most don't. Beta 1, beta 2. So beta 1, that goes with ADA. And that's just because that's the order in this table. And it's pretty much going to go in whatever order the folks put it in the model. So here. Sorry. So that will be our null and alternative hypothesis. So now we're going to say, okay, well, we want to look at ADA. We're pretty much going to look just at this row. And you can see, like, there's the t-statistic and the p-value roughly we're supposed to get. Note, this just means less. If you get p and it says 0.000, that means your p-value is less than 0.001. We do not like to say our p-values are equal to 0, because if you say it's equal to 0, it means that what you saw in the sample is literally impossible. However, we saw it in the sample, so we know it's not literally impossible, so we don't like that. So just keep in mind, don't round your p-values down to 0. We will flip out every time, pretty much. So looking here, it's really important. So this would be the population line that we want to estimate. So we have average body fat percentage. X1 is average daily activity. You're more than welcome to write ADA instead of X1 up there. and x2 is sex. And so things to note is you could write ADA and you can write sex here. But if you use x1 and x2, you should label them. Anytime that you have a y or a y hat or an x1 or an x2 or an x3, you should always label what variable that goes with. We will hone right in on that every time. So if I want to go ahead and I want to calculate the t-test statistic, I need to take, this is B1. And that right there, that's SE. So that's my standard error for B1. So I'm going to take the ratio of those two values. And I'm going to get negative 10.42. So looking here, plugging all the values in, negative 0.297 minus 0 over 0.0289. You're going to get, that's my test statistic, or my t statistic. Those are the same thing there. So then you can go ahead, you could take a t table. You're going to find that the p-value is very, very small. It's going to be smaller than whatever the smallest p-value on that table is. So we reject the null hypothesis with a p-value less than 0.001. I got that just from here. At the 0.05 significance level. Once again, there was not a significance level listed here, so we're going to assume 0.05 by default. So a p-value of 0.001 is really small. That's really strong evidence. So there is very strong evidence that average daily activity is a significant predictor of body fat percentage. So we say how strong the evidence is. We say, okay, well, the variable that we're testing, average daily activity, is a significant or is a good predictor, is a useful predictor of, and then whatever the y response variable is. And not only that, after including sex. So after accounting for sex, we still find that it's useful to include average daily activity. So confidence intervals, they're going to be set up basically the same way as they were in simple linear regression. You're going to take the b that goes with the variable of interest times, I like to put parentheses here. It reminds me to do the multiplication first. So times your t star, so your t star critical value for your confidence interval, times the standard error for that variable. And note that t star critical value, your degrees of freedom, they're going to be the same as your degrees of freedom error or your denominator degrees of freedom. They're the same thing. So same as in the last one. And we can get you that formula for the standard error, but it's going to be gnarly. We're never going to expect you to calculate by hand. We will give it to you in the output. So if I wanted to do, let me see real quick, 95% confidence interval for the average daily activity. So I'm looking here. There's my B1. Here's my standard error. I need to find a t star. So I need to know the 95%. So 95%. So my degrees of freedom are same as my denominator degrees of freedom. So n minus p minus 1. This is going to be, there were 14 observations in the sample, so this is going way back to the description. Minus, there are two variables, explanatory variables. We have ADA and we have sex. Minus 1. So we're going to get 12 minus 1, that's going to be 11. So that tells me which row to use. So I'm lining them up. So my T star critical value for this is going to be 2.201. And that's going to be where it came from. So plugging in here, take all those values, so negative 0.297 plus or minus, here's my T star that we just calculated or got from the table, times that standard error. So go ahead, do your multiplication first. Things will go sideways very quickly if you don't do multiplication first. After that, go ahead, do your adding and subtracting. End up getting a 95% confidence interval of negative 0.361 to negative 2.233. Note that these are both negative. That means that 0 is not in the interval. If 0 were in the interval, that means I would have failed to reject whether or not ADA was useful, because 0 would have been a possible or a plausible value for it. But here, it looks like no, we don't think 0 is a plausible value. In fact, we think that, the higher the ADA goes, the lower the body fat percentage goes. That's why it's negative. It decreases the body fat percentage. So then we're going to write this up. So just a reminder, because I, have issues remembering from slide to slide all the values. This is going to be really, really similar to the slope write-up that we had for last week, except for we need to mention while holding sex constant. So sex is the other explanatory variable. We need to hold that constant. So while holding sex constant, so you don't want to mix and match like, oh, we have, a male individual with 60 minutes of average daily activity and a female individual with 61 minutes. You don't want to do that. You want to have a male and a male or a female and a female. You don't want to mix and match there. So this is new. So while holding sex constant, the 95% confidence interval for the slope of average daily activity estimates that for each additional 1 minute of daily activity, body fat percentage is estimated to decrease by 0.23% to 0.36% on average. Is there more? Oh, with a point estimate, yeah. I was going to say with that comma. With a point estimate of 0.295 decrease. And these are decreases because those values are negative. If those values were positive, it would be associated with an increase in body fat percentage. So this is going to be basically identical to if you had a confidence interval for a slope coefficient in simple linear regression, except you're going to add while holding whatever other explanatory variables constant. And we're going to want you to name them. So if I had, it would have been goofy to have height. But if we had height, if we had, age, while holding age, height, and sex constant, we expect that body fat percentage decreases when this happens, that kind of thing. So residuals plots. So they're going to be calculated the same way. There's extra steps. They're going to be the same assumptions though. Like we'll put them together in a plot for you. We don't expect you to create the residuals plots. You're going to look for, hey, are there curved shapes? If so, then fitting this line doesn't help. We needed to fit a curve. If you have fanning out or funneling in the residuals plot, that tells me, hey, this line's not consistently good. We don't have constant variance or constant spread. It means the line's better in some places than in others, and we don't like that. Definitely, those are going to be the key things that you look for in a residuals plot. So we want to know, hey, are they normally distributed with a mean of 0 and a standard deviation of sigma? This sounds really, really complicated. Just know that we want to know that around the lines, the points are denser close to the line, and they're less dense further away. We want to know that, the line on average does pretty good. You don't want all the points to be hanging out away from the line. The observations are independent. You're not going to find this necessarily from the residuals plot. This is going to be like, you need to know how these individuals were sampled and are they related to each other? Is the result from one of them likely to affect the result from another? Like, you probably wouldn't want to take individuals from the same household. Or you probably wouldn't want to take twins or siblings, that kind of thing. You don't want family members, basically. The variation is constant, so no fanning out or funneling in. The relationship is linear, so no curves, shapes in the residuals. So checking assumptions, plot the residuals. We're going to pretty much, anytime we want you to check these assumptions, we'll provide this plot for you. And basically, if there's roughly even random scatter in this plot that's centered around 0, we're happy. We're happy with nice, roughly even random scatter. So here are the residuals for the body fat example. So know that however many observations in your sample, that's how many residuals you have. Every single observation has its own residual. So there should be 14. So looking here, I mean, I would argue it's roughly even. Like, yes, there's fewer out here, but spread-wise, I wouldn't say it goes wildly different. I wouldn't say there's a big curve in there. I would say linearity's okay. In general, we're going to usually assume normality is okay. It's going to look really funny if it's not. It's going to be like all the points are really dense in one place and less dense. You want that to be dense around the middle, basically. So, yes, I'm going to argue yes. Because roughly even, random scatter around 0. With no curves or fanning out or funneling in. So prediction and estimation, just like with simple linear regression, we can go ahead and say, okay, for, a person with specific characteristics, so maybe they are female with 60 minutes of average daily activity, we can estimate what one individual, like what their BMI would be, or we can estimate the average for all females with 60 minutes of daily activity from that population. Know that calculating them is tedious, but confidence, it's going to be the same as with the simple linear regression, that's the average for the entire population with that specific set of characteristics. It's going to be narrower. The prediction, it's for an individual. Individuals vary more than the average for everybody does. It's going to be wider. So if we give you 2 intervals and say, oh gosh darn, we forgot to label them, which one is which, just identify which one's wider. That one's the prediction. Whichever one's narrower, that's the confidence interval. So like here's an example where we have just we have our least squares regression line for estimated body fat, but we want to estimate the body fat percentage for a male, so that's a value of 1. Average daily activity, 60 minutes. So that's saying I need to plug in 60 here. I need to plug in 1 here for sex. Remember, if it was female, you plug in 0 for sex. It's just because they're alphabetically in that order. So plug that in. Remember to do the multiplication first. Things will go sideways if you don't. And end up getting 22.3%. So basically, this is just our point estimate. This isn't an interval estimate, but if we wanted to use our least squares regression line to estimate the body fat percentage of a male that exercises 60 minutes a day, we would estimate based on our line their body fat percentage would be 22.3%. So we like to joke, this is really just the tip of the iceberg. I cannot even begin to tell you, like, just if you're looking at multiple linear regression, how very much this is the tip of the iceberg. We could spend weeks on multiple linear regression alone. We are just kind of throwing, like, here are the basics in 202. Absolutely, practice helps. This is really just, there's so much beyond this. So there's transformations, there's all sorts of goofy things. Absolutely comment if you have questions or whatnot on what we are covering. But there are a lot of rabbit holes we could go down here. So just know it could get more complicated. We aren't going to go there, though. I think that is it. So that's it for not just multiple linear regression, but it in terms of our notes. I might throw in an example video showing how indicator variables work, just because they can be a little tricky. So I look forward to talking with y'all on the discussion boards.